The year is 2050, and at first glance, it feels like just another ordinary night. You flip a light switch, charge your car, and stream a movie, and nothing feels different. But most of that power isn't coming from a wind farm or a solar field. It's coming from giant solar farms in space, beaming energy down to Earth in invisible waves. Now imagine the headlines the first time one of those orbital power stations goes offline. Is it a glitch, a cyber attack, a space laser conspiracy, or just physics and economics finally catching up? In this video, we're going to cut through the hype and the fear. What does the science actually say about space-based solar power, and could it ever beat normal solar and wind on cost? By the end, you'll know whether this is our energy future or just beautiful sci-fi that doesn't add up. Space-based solar power, often shortened to SBSP, is a simple idea with insanely hard engineering. Instead of putting solar panels on your roof or in a desert, you put them in orbit. They sit above the clouds, above the weather, and collect sunlight almost all the time. Then they convert that energy to microwaves or lasers, beam it down to a big receiving antenna on Earth, and turn it back into electricity. Up in geostationary orbit, about 36,000 kilometers above the equator, satellites see near constant sunlight. Some designs can be lit more than 99% of the time, compared to maybe 25 to 30% of the day for ground solar, once you include clouds and night. So on paper, SBSP promises three big upgrades. It can capture more sunlight, it can operate almost 24 hours a day, and it can point power wherever it is needed most. That is why NASA, space agencies, universities, and even defense departments keep coming back to this idea. The good news is that the physics on the collection side is amazing. Above the atmosphere, sunlight is stronger than it is at the surface, before clouds, dust, and haze steal energy. On Earth, solar farms may only deliver useful power a third of the time. In orbit, a satellite in the right orbit could deliver power almost all the time, with only brief eclipses near equinoxes. Then there is wireless power transmission. This sounds like magic, but we have already tested it. In one demonstration in Japan, engineers beamed kilowatts of power as microwaves over tens of meters on Earth and converted it back to electricity with high accuracy. In 2023, a Caltech experiment called the Space Solar Power Demonstrator went one step further. It carried solar hardware into orbit and showed that power could be wirelessly transmitted in space and even detected back on Earth. So the basic chain of events is already proven in small experiments. You collect sunlight in space, convert it, beam it, and receive it. The core physics is not science fiction. But that is not the hard part. The hard part is scaling this up to gigawatts, the kind of power a country actually needs. And that is where the story flips. To deliver serious grid power, you don't just need a satellite. You need a flying power plant the size of a small city. A detailed NASA analysis looked at reference designs that would each deliver about 2 gigawatts of power to the grid, roughly 2 large nuclear reactors worth. Even the lighter design needs millions of kilograms of hardware in orbit and thousands of heavy lift launches to build. Launch costs alone swallow most of the total bill. Then there's the beam itself. Microwaves spread out like a flashlight beam. To keep the intensity safe at the ground, engineers design a very wide beam, kilometers across, and a huge receiving antenna farm to catch it. Typical commercial concepts aim for a power density around the level of strong sunlight near the center, but that central area would be fenced off as restricted industrial space. That means you're building giant structures in orbit and giant antennas on the ground, all of which must point with extreme accuracy so you don't miss the target by a small angle. Japanese teams have been testing high-precision beam pointing control and report extremely small angle errors in lab systems, which is impressive, but scaling that to geostationary orbit is another challenge. So the engineering verdict is not impossible, but huge. And huge in space usually means very expensive. Now for the part everyone secretly cares about. Does this ever make economic sense? In that same NASA study, researchers calculated the levelized cost of electricity, or ELSI, for their 2 gigawatt space power designs. That's the average cost per kilowatt hour over the system's life. Their baseline numbers came out around several cents to more than $1 per kilowatt hour. For comparison, typical households in the United States in recent years paid under 20 cents per kilowatt hour, and projected costs for future land-based renewables like wind and solar with storage are in the few cents range. In other words, in the baseline scenario, space power was roughly 10 to 80 times more expensive than just building more solar and wind on Earth. But here's the twist. When NASA and other researchers played what if with multiple assumptions, such as cheaper launch, better manufacturing, more efficient propulsion, and longer lifetimes, they found an optimistic case where cost drops to just a few cents per kilowatt hour, potentially competitive with terrestrial renewables. So economically, the answer isn't a simple yes or no. It's more like only if we rewrite the rules of space launch and manufacturing. Whenever you mention beaming power from space, the internet does what the internet does. You'll find claims that SBSP is really a weapon in disguise, a space laser for burning cities, changing the weather, or even controlling minds. Let's separate physics from fear.
First, safety standards. In many countries, worker safety rules for microwave exposure set limits on how much continuous power people can be exposed to. Commercial SBSP concepts are designed so that the beam intensity at the ground is around solar-like levels in the central receiving area and much lower outside. People and aircraft are kept out of the highest power zone with fences and airspace control, much like existing radio and radar sites. Could the technology be misused? In theory, any powerful energy system has dual-use potential, and older studies have noted that very high-intensity beams could be harmful if badly designed or deliberately mispointed. That is one reason regulators and defense experts watch these projects closely. But the popular idea of a pinpoint death ray that can silently pick off targets worldwide does not match the actual beam sizes, power densities, and physics of how microwaves spread. These beams are wide, regulated, and very obvious to anyone who monitors radio frequencies. So yes, engineers and regulators take safety and dual-use issues seriously. But most of the wilder conspiracy theories say more about our fears than about what SBSP designs are actually intended to do. And here is the really weird part. The biggest risk is not that SBSP cooks people. It is that it cooks investors' money if the economics do not work. Even with all those caveats, several countries are pushing ahead. Japan has spent decades on wireless power transmission. Researchers there have already demonstrated kilowatt-scale microwave beaming on the ground and are planning small orbital demos, moving step by step toward possible megawatt or gigawatt-class systems. Caltech launched its space solar power demonstrator early in 2023 and reported successful wireless power transmission in space and detectable power beam to Earth before the mission wrapped up. The European Space Agency is running the Solaris Initiative, a program to study whether large constellations of space solar satellites could back up Europe's renewables and reduce dependence on fossil fuels. ESA aims to inform a go or no-go decision on bigger investments around this decade. The United Kingdom funded an independent study that concluded SBSP is technically feasible and could provide significant capacity by mid-century for the UK alone, if development goes well. The government has since put money into a space-based solar power innovation competition, seeding companies that are working on key components. In 2025, researchers at King's College London modeled a future European grid and found that adding SBSP based on NASA designs could, in theory, cover a large share of Europe's renewable energy needs, cut grid costs, and dramatically reduce the need for battery storage, assuming aggressive technology progress. Some commentators now argue that with falling launch costs and new designs, space solar is finally technically and economically viable in specific scenarios, though that claim is still debated in the wider research community. So this is not just sci-fi anymore. It's a real global race, but one where the finish line keeps moving as we learn more. Now, what happens if it actually works? In a successful future, you would have orbiting power islands that can send clean electricity almost anywhere on Earth with minimal weather impact. In places with little land for renewables, or in regions that want to reduce dependence on imported fuel, that would be huge. Models suggest that if the costs come down enough, SBSP could take pressure off massive land-based solar and wind buildouts, shrink the need for huge battery farms, and provide a stable backbone for a mostly renewable grid. Geopolitically, countries that master SBSP might gain a new kind of energy from orbit influence, similar to how oil and gas exporters shape today's world. That's exciting for some, worrying for others, and almost guaranteed to be wrapped in politics. Environmentally, analyses suggest that the lifetime carbon footprint of SBSP, once you account for hardware and operations, could be in the same low range as wind and solar, and far below coal or gas, especially if launch vehicles themselves get cleaner over time. So if we can tame the cost and manage the risks, SBSP becomes less of a crazy idea and more of one tool in a much bigger clean energy toolbox. So what do the physics and economics really say about space-based solar power? On the physics side, the core idea works. We have already beamed power on Earth and in space, and there is nothing in basic physics that blocks scaling it up. On the engineering side, it's massive. We're talking about building structures with millions of kilograms of hardware and controlling kilometer-scale beams with extreme precision. That's hard, but not obviously impossible. On the economic side, right now, it's not competitive with building more solar and wind on Earth, but multiple studies show that with cheaper launch, better materials, and mass production, the cost could fall into a range where SBSP becomes attractive in specific roles. And on the myth versus reality side, it's not a magic free energy machine, and it's not a sci-fi death ray. It's a complicated, expensive, but potentially powerful way to move clean energy around the planet. In the end, space-based solar power is neither a guaranteed savior nor an obvious scam. It's a high-risk, high-reward bet on our ability to make space cheap, build big things in orbit, and treat energy from space as a shared global infrastructure rather than a new source of conflict. If we get that mix right, the most surprising part of SBSP might not be that we can beam power from orbit. It might be that one day you'll flip a switch, the lights will come on, and you won't even think about the giant solar farm quietly glowing above your head.